So welcome everybody in this afternoon session of, unfortunately, our final day here in this very interesting conference here in the Riemann International School of Mathematics. We have two speakers this afternoon. Unfortunately, the first speaker is not present here because for COVID reasons, but she's spiritually present and also technically present due to the magic of Zoom. So it is a pleasure to introduce Beatrice Langella from the SIS in Trieste, and she will talk about the growth of Sobolev norms in quasi-integrable quantum systems. So please, Beatrice, the stage is yours.
Okay. So first of all, thank you very much to the organizers for the very kind invitation. Of course, also I would like to thank them very much for all their patience in supporting me with all these little bit of health inconveniences. So today I would like to talk to you about the result of growth of Sobolev norms in a class of systems, which we call quasi-integrable quantum systems, and I would like to present it to you as a quantum version of a Nekrashev theorem. And this is a joint work with Dario Bambusi. Okay, so this is the general plan of the talk. First of all, I would like to introduce you the abstract model that we deal with, namely this class of quasi-integral quantum systems. Then I would like to list you what are the main concrete applications that fall under this umbrella of quasi-integrable quantum systems. Then I would like to go on giving you a precise, rigorous statement of the main result. And in the last part of the talk, I would like to give you a sketch of the proof, which resembles the one of the Nekrashev theorem for classical dynamical systems. And as the proof of classical Nekrashev theorem, it is divided in two parts, an analytic one and a geometric one. Okay, so first of all, what model are we dealing with? We study an abstract linear Schrödinger equation on an abstract Hilbert space H of the following form: I psi dot time derivative of psi equals H naught applied to psi plus a perturbation V of t applied to psi, where H naught is an unbounded self-adjoint operator, and actually we assume it to be a pseudo-differential operator of order d strictly larger than 1, but you can think of a differential operator of order d larger than 1, and it will be the Hamiltonian of what we will call a globally integrable quantum system. And concerning the perturbation V of t will be allowed to be a family of self-adjoint unbounded operators and with smooth dependence on time. And they also will be pseudo-differential operators, but of order, think of the order as order of differential operators, be strictly less than the order of a main operator. And I will actually spend a few slides giving you a definition of what do we mean with a globally integrable quantum system. But before going on, I would like to give you a very rough and simple idea so that you have something in mind to think of. Okay, in a classical case, if I have a H naught, small h naught, which is the Hamiltonian of an Hamiltonian system which we know to be globally integrable, then in such a case, we know that if it's globally integrable, we know that there exist action variables, say 1 up to AD, such that I can write my Hamiltonian as a function of the actions only. And here we decided to borrow this property of classical Hamiltonians into the quantum world, say into the quantum setting. And so to speak, we say that H naught, capital H naught, is the Hamiltonian of a globally integrable quantum system if there exist not functions, not actions, but operators, A1 up to AD, with certain properties that will be clear later, that I will define later, such that I can write my operator, capital H naught, as a function of these quantum action operators only. Okay, so what about the result that we consider? Okay, we have a result of upper bounds on the growth of Sobolev norms of all the solutions of these Schrödinger equations. Namely, we consider a suitable scale of Hilbert spaces HS, each one labeled with equipped with its norm, which we denote by lower index S. And what we prove is the following: take any initial datum psi naught, which belongs to the Sobolev space HS, then the S norm at time t for any t real of the solution is bounded up to a constant by the norm of the initial datum times a factor t to the epsilon, no matter how small epsilon is. So we have this kind of very weak upper bounds. And the proof is inspired by the proof of the classical Nekoroshev theorem. And as the proof of a classical Nekoroshev theorem, as I mentioned before, it is based on two steps. There's the first step, which is based on an analytic normal form. And then there's the second step, which consists in making a refined geometric analysis of the normal form that one has, in order to understand the resonances, the geometric structure of the resonances that are hidden inside the problem. And before going on, I would like to spend at least a couple of words on the physical meaning of a result of growth of Sobolev norms. And Filippo in his talk already mentioned something about it, but just let me say a couple of very elementary things. As an example, think of HS as the standard Sobolev spaces generated by the Laplacian on the d-dimensional torus TD. Then if we are on the d-dimensional torus, we have at our disposal Fourier representation with respect to x variable. So I can represent like that any function psi. And of course, I have that the Sobolev norm of a function psi can be represented in this way as a sum over the frequency keys, modulo square of the Fourier coefficients times key to the 2s. And I said we have self-adjoint structure in our problems. And so when we have self-adjoint structure in this class of problems, this implies that the L2 norms, so the H0 norms, are conserved. I mean, this quantity is constant for any time. And so, of course, if I have that the T norm grows in time, this means since the S norms, these norms, as the difference with respect to this one is that the S norms weights more the higher Fourier coefficients because of these coefficients key to the S. If I have growth in time of Sobolev norms, this means that the energy is transferring from the lower to the higher Fourier modes. And so what's the physical interpretation of this result? The physical interpretation is that the particle absorbs energy from the system. But, look at our result. This bound, the growth that we are allowed to have is very weak because it is only less or equal than t to the epsilon for any epsilon. And so what we have is that we can appreciate this transfer of energy. So now let me talk about the applications that we can deal with within this class of models. First application that we can deal with are the Laplacian is the case of perturbation of the Laplacian on the d-dimensional flat torus. This means that one, as I told, considers the Schrödinger equation I psi dot equals minus Laplacian applied to psi plus a perturbation V of t. This class of perturbation V of t is a class of perturbation that we assume to be infinity and bounded with respect to time, and they are allowed to belong to the class of to a particular class of pseudo-differential operators, which are called pseudo-differential operators in Ormander class of order B strictly less than 2. And as I said, this is okay if you're familiar with pseudo-differential operators. In case you are not familiar, you can simply think of differential operators of order 0 or namely multiplication operators by a function, or differential operators of order 1, which are inside this class. So for instance, a physically interesting class of perturbations that here we can deal with is the following: V of t equals I space the derivative with respect to space times a of t of x plus b of t of x for a and b, which are two infinity and bounded with respect to r capital times td. Are valued, and this class of perturbation covers the case of of a particle moving in a periodic time-dependent electromagnetic vector field. And for instance, in this case, the class of Sobolev spaces that we consider are the standard ones generated by the Laplacian. And of course, in particular, the result we obtain, as I mentioned, is for all these class of perturbations, we have t to the epsilon upper bounds for any t and for any initial datum. Application number 2 that we can deal with is the following one. The previous one is a particular case of a Schrödinger equation where the main operator is the Laplace-Beltrami operator on a compact Riemannian manifold with integrable geodesic flow. So more in general, let me consider this class of Schrödinger equations. I partial time derivative with respect to psi equals Laplace-Beltrami operator applied to psi plus v of t, where v of t is, again, a time-dependent family of pseudo-differential operators in Ormander class, as before. And as before, HS is the standard scale of Sobolev spaces. But as before, you can think of v of t as a class of differential operators of order 0 or of order 1. And under these assumptions, the cases we cover are the following one. First, PD we cover Schrödinger equation, where in the case where M is a two-dimensional rotationally invariant manifold with the revolution metric, which is given by this expression G equals A of sigma d theta square plus d sigma square, where this A of sigma parameterizes this profile. And we have to suppose that A admits at most a critical point, sigma naught, and such critical point has to be non-degenerate, namely second derivative. We ask that it is different from 0. So this is a case that we can cover. Another case that we can cover is the following one, the one where M is a simply connected and compact Lie group equipped with its B-invariant metric. And for instance, examples are simply connected and compact Lie groups are the specially unitary group SUN, or the compact version of the symplectic groups as E of n, or the compact version of the spin groups spin of n, and so on. Another case that we can cover is the case where M is a Zoll manifold of arbitrary dimension, namely a manifold whose all geodesics are closed, and for instance, you can think of the sphere. And again, in this case, we obtain the following result: T to the epsilon upper bound for any T and for any initial datum. And finally, in the cases where M is the torus or a compact Lie group or a Zoll manifold, we can also cover the case of n identical particles on the same manifold, possibly interacting. Okay, third application that we can cover is the anharmonic oscillator in dimension 2. So let me consider the following equation: I partial time derivative of psi equals h naught plus perturbation v of t, where this time h naught is the Hamiltonian of the quantum anharmonic oscillator, which means h naught equals minus Laplacian, okay, times 1/2, plus a potential, which is x to the 2L over 2L. Now, and we consider this equation on L2 over 2. And in the case where L is equal 1, you recognize the Hamiltonian of the quantum harmonic oscillator. But here we deal with the case, much less known, of a positive integer L strictly larger than 1. And v of t, again, is allowed to be a smooth and time-dependent family of self-adjoint operators. And again, we can take them to be in a particular pseudo-differential class, which is the class of L-Ferrobert operators of order b strictly less than this number, 2L over L plus 1, which is the order of this operator h naught as an L-Ferrobert pseudo-differential operator. But again, if you're not familiar with the pseudo-differential operator, you can think of this example of a class of allowed perturbations, namely v of t equals c of t, a smooth and unbounded function of time, times x1, position variable, times I partial derivative with respect to x1 plus I partial derivative with respect to x2. This is an example of a class of admissible perturbation. And in this case, the scale of Sobolev spaces that we consider is the natural one associated with this unperturbed operator h naught, namely instead of the Laplacian and taking the Sobolev spaces generated by the Laplacian, we take the Sobolev spaces generated by h naught to this power L plus 1 over 2L. And again, in this case, from our abstract result, we deduce the T to the epsilon upper bound for all Sobolev norms, all times, and all initial data. Okay, and before going on, just let me talk about a little background. And of course, here I will not mention anything about the beautiful results that, for instance, Filippo mentioned on the nonlinear Schrödinger equations. And another thing I will not mention is the beautiful results that do exist also in the linear case, but for lower bounds. So there are actually beautiful results where people show also in the linear case that these solutions actually grow for some examples in time. Here I will only stick with the case of upper bounds and for linear Schrödinger equations. Okay, so main reference is the work by Bourgain, where the T to the epsilon upper bound is proven for the Laplacian and torus in a case of bounded perturbation V of T. And the technique uses a lemma of separation properties of the Laplacian, which is highly specific on the torus, and was later generalized by Delors to the case of rotational invariant surfaces in dimension 2, and then by Berti and Maspero to the case of arbitrary flattori, but always in a case of bounded perturbations V of T. And in a case of another case that has been covered is the case of the Laplacian on manifolds. In such a case, the T to the epsilon upper bound was already obtained as a consequence of the abstract work by Bambusi, Greber, Maspero, and Robert, exploiting the fact that the classical flow is periodic. And concerning the case of the anharmonic oscillator, no T to the epsilon bound was known, not even in the case of bounded perturbations V of T. Only result that was known for bounded perturbation V of T was a T to the S upper bound, so a weaker bound, which follows from the abstract work by Maspero and Robert. And so, to summarize, in some sense, what we obtain is that we enclose in a unique framework all the previously treated models for which T to the epsilon upper bounds are exhibited in a case of pseudo-differential operators of order D strictly greater than 1. And we also found new ones, such as the case of the harmonic oscillator and a case of Lie groups. And we also extend always the theory in order to case not only the case of bounded, in order to cover not only the case of bounded perturbations, but the case of perturbation with, say, the maximal order. Okay, so now just let me say a couple of things about the statement of the main result. I need some assumptions, and the first assumption is a little bit technical, but I will try to simplify it as much as possible. First thing is that we fix an operator K0 with compact inverse, and we define HS as the subole space is generated by K0 to the S. And our aim here will be that we want to deal with a setting which recreates as much as possible all the property of pseudo-differential operators. And again, you can think of differential operators, and most of the properties are shared also by differential operators. First thing that we want to do is that we want to define the concept of order of an operator. So we want to define the set AM, the class AM of operators of order M. And for instance, you can think of differential operators of order M. So what we ask is that this operator K0 to the M is a differential operator of order M. For instance, the Laplacian to the 1/2 is a differential operator of order 1. Then we want that if we call an operator of order M, it extracts M derivatives, namely it is bounded from HS to HS minus M for any S. Then we want inclusion properties to hold, namely we want that if an operator is of order M, it is also of order M prime, provided M prime is larger than M. We want that it is an operator is of order M, also its adjoint is of order M. We want to be able to compute the sum of two operators of order M and say that the sum is of order M. We want to be able to compute the composition of two operators, one of order M and the other one of order N. We want to be able to say that the product, the composition is of order M plus N. And then this, say, very typical and characterizing property of pseudo-differential operators, which is the commutator gain. Namely, if I do not compute the product of two operators, but I compute the commutator, instead of finding an operator which is of order M plus N, I obtain an operator which is of order M plus N minus 1. So I gain 1 from the commutator, from taking commutators. And the last two properties, maybe I just let them appear on the screen, but I will not comment on that. They are more technical and they are more typical of pseudo-differential operators. Now I want to focus on the commutator gain property, because actually, to be precise, we are not able to ask this property, but we want to ask a slightly weaker one. Namely, maybe we will not be able to gain exactly 1 when taking commutators, but maybe we will be only able of gaining a factor rho, with rho strictly less than 1. And so I put two labels on my class of operators, M, which is the order, and rho, which is how much do I gain from the commutator. But in any case, take away message, we want to deal with a setting which recreates properties of pseudo-differential operators. Now, just let me come to the maybe more interesting properties, more typical assumptions that we made. We want to define, as I anticipated, the quantum analog of action variables. And thus, we require the following. We require that there exist D pairwise commuting self-adjoint operators A1 up to AD, which are operators of order 1 in the sense that we defined before. And okay, they commute, and furthermore, we ask that they have pure point spectrum. So in particular, they have a common basis of eigenfunction, and this means that we can define the joint spectrum lambda of A1AD as the set of d tuples A1 up to AD, such that there exists a common eigenfunction psi, which is eigenfunction of A1 related to the first number A1, small a1, of A2 related to the second eigenvalue, small a2, and so on up to d. So this joint spectrum is the collection of d tuples of eigenvalues of the operators A1AD. And what we ask on this operator is that their joint spectrum satisfies the following property. First one, it is contained in a lattice ZD, possibly translated by a constant kappa. And second one, it is contained into a cone. So we ask that the joint spectrum is contained in the intersection between a cone and this translated lattice ZD. And these two, again, are a little bit more technical assumptions. We ask ellipticity for the operator sum over j of the squares of the AJ. And we want that if f is a function with a certain growth properties, then we can build the functions f of a1 up to ad for the operators A1AD, and this function f of A1AD still is in a good class of operators of order m. Okay, so now we want to relate these operators A1AD to our unperturbed operator H0, and this is our definition of globally integrable quantum system. We say that H0 is a globally integrable quantum system if there exists a smooth function small h0 and the operators A1AD with the property that I said you before, such that I can write H0 as a function, smooth function H0, small h0 of these operators A1AD. Okay, maybe a natural question at this point is, okay, but are these natural assumptions? And given an operator H0, how do I verify them? Are they easy assumptions to verify or not? Okay, so I would like to comment on this, and so let me make a little step back, a small step back. Just let me say a couple of things about pseudo-differential operators. Okay, the general idea before pseudo-differential setting is the following one. Recall the well-known quantization rule, which enables you to pass from a position variable to the operator, which is multiplication operator by x, and the momentum variable, it is quantized as the derivative operator with respect to x. Okay, pseudo-differential calculus generalizes the above quantization rule, and in particular, this means that it enables us to build a map between symbols, namely smooth functions of x position and p momentum, with values into a certain class of linear operators, which we call the pseudo-differential operators. And of course, this function will have to have suitable growth properties. And here I wrote you an example of how this map from symbols, so from functions, so from classical Hamiltonians to quantum Hamiltonians operators works. This is the case of the case of the quantization map. How does it work on Rn? But it was only to be concrete. And of course, to symbols, to functions with different growth properties, we have that correspond different classes of pseudo-differential operators, for instance, the ones I mentioned you before. But the general idea, the takeaway message is when we have to do with pseudo-differential operators, we always have a way to recover from the quantum operators the classical system, a classical system which is hidden inside, which is strictly related to this quantum problem, and it is the one with the classical Hamiltonian given by the symbol associated to our quantum operator. So we always have a way to pass from a quantum system to a classical one. Okay, and so one of the possibilities, but this will not always be the case, and for instance, in the case of Lie groups, it turns out that this is not the case, but here I will not talk about this. One of the possibilities, if I have to solve this problem, so I have an operator H0, and I want to say, to determine if it is quantum integrable or not, namely I want to find quantum actions for H0, one of the possibilities is the following one. I recover the classical system hidden inside H0, namely, I consider the classical symbol associated to H0. I find classical action variables, A1 up to AD, for the Hamiltonian H0. I quantize them, namely, I again use the map in the other sense. I construct the quantization of A1 up to AD, and I hope that I have found quantum action variables for H0. And first example where one can do this, and this actually works, is the case where capital H0 is the Laplacian on the torus. In this case, of course, if you recall this well-known quantization rule, you immediately obtained the fact that minus Laplacian is the quantization of the classical Hamiltonian p square. And since we are on the torus, the conjugate variables to the momentum p are already angles, and so it is already an Hamiltonian in action variable, so with actions a1 equals p1 up to ad equals ad, pd. And in this case, we already have that these actions live in a degenerate cone, which is the whole space Rd. And what about the quantum actions? So we simply quantize the classical actions that we find. We again recall the quantization rule with which to P1 associates the partial space derivative with respect to x1 and so on. And we easily obtain that these are our quantum action operators. And in particular, in fact, the Laplacian can be expressed as modulus square of I, the space derivatives, the gradient. The second example where this holds is the case of the enharmonic in dimension 2. In this case, we have said that the unperturbed operator is the Laplacian plus x to the 2L over 2L, and it is the quantization, again using the same quantization rule, of the Hamiltonian p to the square over 2 plus the potential x to the 2L over 2L. And again, so first step, we have said, according to the scheme I told you before, we want to find classical actions for our Hamiltonian H0. And so one passes to polar coordinates and has a radius variable and angular variable and the conjugate momenta, and one obtains this nice representation for the classical Hamiltonian. And one easily computes the actions in the standard way, constructing the loops around the the loops, integrating along loops the P R and P theta actions. And first action, we actually called it PA2, is the angular momentum P theta, x1 xi2 minus x2 xi1. And the other, the radial action, has this expression. But it has this problem. The radial action has a singularity at p theta equals 0. So the first action that we find it is smooth. The second action that we find has a problem because it has a singularity, and we do not want to deal with singularity. But fortunately, in the two-dimensional case, there is an easy way to overcome this lack of regularity. Namely, we define an action A1, which is the previous one AR, if p theta is greater than 0, and we translate it simply. We define it as AR minus p theta if p theta is less than 0. And with this construction, it turns out that A1 and A2 are smooth functions. Actually, they are analytic, and they actually live in a following cone that I draw you in, that I pictured in blue with respect to the plane A2, A1. And concerning the quantization, we have a very nice work by Colin de Verdier, which guarantees us the following. If we compute the quantization of these two actions, A1 and A2, then up to lower order terms, we found some nice quantum action operators, A1 and A2, which actually have the nice properties on the discrete joint spectrum that I mentioned you. And this is actually a particular case of a much more general fact. And there are some works by D'Oystermatt and Guillemin, by Colin de Verdier, and also by Alfer and Robert, which in some sense guarantee you, exhibit some nice examples of cases where if you quantize action variables that have to exist globally, then you have that the quantization enjoys the nice spectral properties that I mentioned and that we assumed. Okay, so now I have decided, I'm sorry. Now I have defined what do I mean with a global integrable quantum system, and I would like to impose some properties on H0. And as in the case of the small function H0, and as in the case of the classical Nekrashev theorem, we require that H0 is a steep function. And of course, here I reported you the definition of a steep function, but if you're not familiar with that, it's not even necessary that you read it. Just say, okay, first things to bear in mind is that if we define omega as the gradient of the Hamiltonian, we want it to never annihilate. And then we have this nice non-degeneracy property of the on the gradient of the Hamiltonian H0. But it is not necessary actually that you read with precision this definition, what is necessary to remind is that convex functions and quasi-convex functions are always an example of steep functions, and furthermore, that steepness is a generic property with respect to this infinity topology, as was proven by Nekurashev in one of his works in '73. And another case, another thing I would like to write, to point out, is that we have a beautiful criterion, which is due to a nice work by Riemann in 2006, which is the one that we actually exploited in applications, namely the following one. If H naught is also an analytic function, we have a nice criterion to verify, to check if it's steep or not. Namely, it is sufficient to check that its gradient does never annihilate, and if we compute the restriction of the Hamiltonian to any affine linear subspace, then it only has isolated critical points. And so an example of a steep function, just to be clear, a1 to the square plus a2 to the square, of course, because it's convex. An example of a non-steep function, a1 to the square minus a2 to the square, because it vanishes on these two hyperplanes. Furthermore, we do not only ask steepness, but we also ask homogeneity of the function h naught. Namely, if you compute it into lambda a1 up to lambda ad for lambda positive parameter, it equals lambda to the d times h naught computed in a1 ad, and we only ask this property out of a neighborhood of the origin. Okay, so summarizing, these are the assumptions that we ask. We ask that h naught is a global integral quantum system, namely I can write it as in terms of suitable action operators. We ask that it is homogeneous of degree d greater than 1 at infinity, and we do not require that h naught is steep on the whole cone C, which contains the joint spectrum of A1 AD, because this would be a too much strong assumption. But we only are satisfied with asking that steepness hold inside the intersection of the cone between an annulus, which is the one contained between the ball of radius 2 and the ball of radius 1 alpha. So maybe picture needed. If this is the representation of the joint spectrum lambda, where the spectrum of the actions A1 AD is contained, we ask that H naught is homogeneous and that it is steep inside this yellow region, which contains this circular annulus. And under these assumptions, what we actually have is that we can prove that if we are in this setting, then for any v, it's infinity unbounded with respect to time, with values inside the differential operators where there b and b less than d, we have actually our t to the epsilon upper bound. So I would like now to give you to say a couple of words about the proof of the result. So the result is based on a normal form technique, and in particular, our goal is to conjugate our initial Schrödinger equation to a new Schrödinger equation, which has the following form: same unperturbed operator, plus a normal form part which we call Zn, plus a remainder term which has to be smoothing. Namely, in particular, we will neglect it. It will be neglectable because it maps S subole spaces into a S plus n subole spaces for any S, and with a fixed n, which will allow to be arbitrarily big. And so our mechanism of the proof is the following one. If we are able to conjugate the starting Schrödinger equation to this new Schrödinger equation, and if, neglecting the remainder term, we are able to prove that for this truncated Schrödinger equation, we have that subole norms are uniformly bounded in time, then it is easy to prove that the addition of the contribution of the smoothing remainder term does not spoil the growth of Sobolev results, the growth of Sobolev norms result that we obtain, and it is easy to prove the t to the epsilon upper bound. So our goal is to conjugate our system to a Schrödinger equation like this. And of course, we will do it iteratively, and it turns out that we will manage to perform, thanks to the pseudo-differential properties, we will manage to perform this step if to perform this operation, if at any step we are able to get rid of this term, which is the one in red that appears on the screen, and namely to find a particular operator G such that perturbation V of t minus commutator between H naught and the perturbation G of t is equal to a suitable normal form term. So if at any step we are able to solve this equation for G, we are done. And of course, we then can iterate the procedure. Okay, so we are interested in solving this equation, as I said, and here two facts come to help us. First step is that we exploit the lattice structure of the joint spectrum lambda, and this lattice structure is helpful because it helps us define some Fourier coefficients for v of t and g of t. So in particular, we add the fictitious angular variables phi, which lives in TD. We define these operators g of phi and of t, which are nothing else than e to the minus phi dot a is the vector a1, a2 of the quantum action operators, times g of t times e to the I phi dot a. And for this g of phi of t, we have at our disposal, again, Fourier coefficients. And fact two is that we can combine this nice fact of having Fourier coefficients with a nice lemma by Rasmussen, which exploiting pseudo-differential properties enables us to have a nice representation of this commutator between H0 and G in this way. And so this is to say that we reduce our problem of solving this kind of homological equation for G into solving an equation which is nicely, luckily, in Fourier coefficients. So what we want to do is to solve an equation of this form. I, omega evaluated in A, omega is the gradient of H0 times K, times K Fourier coefficients are G, plus V of K of T equals ZK of T for any K, and we want to solve it for G. So what we need to do is to invert these operators omega of A dot K. And so the key idea is that in order to be able to invert these operators, we will divide the sites A1 up to AD into the joint spectrum into resonant or non-resonant sites according to the size of omega of A dot K for any integer key. Of course, the idea is that I can invert the operator if its spectrum is bounded away from 0. So our strategy will be, and this is the nice part because we wanted to invert an operator, but now we have reduced ourselves in order to consider some real quantities, omega of A dot K, and we will divide the sites in the lattice lambda according to this fact. According to the fact is omega of A dot K is bigger than A to a certain power times K, or omega of A dot K is lower than this threshold. Here there is a norm of K missing. And of course, since we have regular operators, we are able to do this division only for values of K which are not too big. Namely, we are able to make an ultraviolet cutoff. And so this means the following. We have our perturbation V of t, which we want to cancel by means of the homological equation. We divide it into three terms. The first one is the term where omega of A dot K, which is the one appearing in this coefficient, is big. So these terms I will be able to cancel them because this operator is invertible. The last line are tails of an ultraviolet cutoff, so they do not matter. And these terms, instead, the ones that I called Z, we will have to keep them because they are normal form terms. And so here I pictured a cartoon in the case where H0 is modulus square of A on the two-dimensional torus. This is the region of lattice point A such that omega of A dot K is less than A to the D minus 1 minus delta for K equals 0, 1. This other one is the region where omega of A dot K is less than this threshold for K equals 1, 1. And of course, these are different possible regions. So we have these parabole like regions where we are not able to solve our homological equation and that we have to keep it. And then in the very last part, just let me tell a couple of words about what do we do with these normal form operators that we are left with. And here is where really the Nekorashev theorem and the classical structure again enters the game, because again we can take inspiration from the classical case, and instead of considering an operator H0 plus D of t, we consider a classical Hamiltonian H0, which is its symbol, and instead of Z of t, just consider a symbol which is supported in this region, the resonant region that I told you, the one labeled with 0.2, that I cannot eliminate. Consider an Hamiltonian, a normal form Hamiltonian that is supported where K, modulus of K, is lower than a certain threshold n, which is A to the epsilon, and omega dot K is lower than a certain threshold mu, which is this quantity that I told you before. And of course, you recognize that in the case where mu or n are fixed numbers, okay, the proof of Nekorashev theorem provides a refined geometric analysis exactly of these regions, and it enables us to prove that they are not too wide and that they are separate from each other. And so our idea was to exploit the geometric analysis of resonances that it is available in a classical case thanks to the proof of Nekorashev theorem, and to adapt this geometric analysis in order to understand what happens, what's the quantum behavior when I consider the quantum operator. And so to summarize, we define a resonant point, a point in the lattice which is below this threshold. And what we do is exactly as in the proof of Nekorashev theorem, we classify the sites according to which resonances affect them, namely according to which are the k's. I take A and I ask what are the k's such that omega of A dot k is small. Now, of course, say in the b-dimensional case, I can have that a site can have no resonances, and these are the sites pictured in blue, or they can have two different linear independent direction of resonances, and these are the case pictured in green, or they can have only one resonant direction, and these are the areas pictured in white. But actually, in this case, we have a foliation, exactly as in the case of classical Nekorashev theorem, into segments which are transverse with respect to the axis of the parabola. And what comes out is that we are able to prove that H0 plus Z as a block diagonal structure which respects this decomposition, this partition into these sets. And so very last step is to use steepness in order to control the size of this segment, and in order to prove that they're separate. And this enables actually us to prove that in the resonant dynamics, the one where I neglect the remainder term, Sobolev norms are actually uniformly bounded in time. Actually, this is due to the fact that we have dyadic blocks. And so we have left with our result. And that was all. So thank you for your attention.